very good morning, one and all. I'm Dr. Malika, Assistant Professor in the Department of Chemical Engineering, BVRIT Narsapur. Today, I'm going to talk about the introduction to Mass Transfer 2. Basically, Mass Transfer 2 subject will come under third year of Chemical Engineering students, where they'll be talking about and understanding more about how exactly a mass transfer operation is very important for a chemical industry perspective. So today's presentation all about the introduction to mass transfer operations, where different types of operations which can be involved in this, we're going to study about it. So basic in mass transfer 2, there are two sections are there, like mass transfer 1 and 2. In 1, we'll study about the basic principles of mass transfer, and along with that we'll talk about the mass transfer coefficients and interface mass transfer we'll deal about. And in mass transfer 1, we'll more into the gas liquid operations like absorption and humidification, and at the end we'll study about drying. This is purely the mass transfer 1 perspective all about. Today's in mass transfer 2, basically we'll talk about the industrial perspective of different equipments which can be used in for the mass transfer operation. Basically, to understand the mass transfer, you should know the driving force for it. Like heat transfer, there is a driving force of temperature difference. In mass transfer, we have the driving force of concentration difference. So there is no reaction in it. There is no reactions involved in it. Only based on the concentration difference, there will be a operation will be happening. For example, when we take a bowl of water, when we add, let's say we are adding sugar or something. Let's say I have included sugar in it. So when we add the sugar, as it has a higher density, it will simply settle down. Let's say I'm adding spoon, I'm mixing this. So now at the bottom you have the more concentration of sugar. So when we use the mixing like agitation, these sugar concentration will move from bottom to the top. This is how the concentration gradient is created. That is how a mass transfer operation will take place. That is a simple example for the mass transfer. So in this, in coming sessions, we'll be talking about distillation operation, liquid extraction, leaching and absorption. Here, depending on the different types of phases which are involved, we'll go with different kind of operations. Basically, these all 4 types are the separation kind of techniques. That's why mass transfer 1 is different from mass transfer 2. Mass transfer 1 will more talk about a gas phase separation, where we'll be doing an absorption kind of. In distillation, we'll deal with different kind of phases. Along with that, we'll talk about how to separate or how to get into the pure form of a product. So, for example, simply take distillation, maybe extraction, leaching and absorption. So first we'll talk about a basic understanding of distillation. Then as we move on to the next sessions, we'll talk about extraction, leaching and absorption. For this mass transfer 2, as we already understood, it's purely of these 4 operations which we are going to deal. And table is a standard book which we can follow to understand mass transfer operations. Along with that, we have Ginkoplis we have, and we have BK Datta. In BK Datta, we can have many problems which you can solve from it. So these are the different reference books which you can follow. So the basic definition of a distillation is it's a kind of unit operation. Simply when we take unit operation and unit process, unit operation, we will not have any chemical reactions involved in it, only operations are there. So those are called as unit operation. Here we'll talk about more into the mass transfer operations. In distillation, the driving force here, we are creating the concentration difference by the addition of a thermal energy. We are trying to boil or heat up the feed which we have, and based on its boiling point, we are trying to separate the components. So if you wanted to do the distillation in industrial level or any level or a pilot scale level, the components, if it's volatile, that will be economical for an industry rather than boiling liquid at 300 degrees Celsius or 500 degrees Celsius. Then we have have to look for the alternatives. Most probably, in using distillation, the separation of volatile components is simpler rather than the other components. So when we heat up the fluid, so we'll create the difference in the boiling point, and boiling point is a function of vapor pressure or the volatility of it. Volatility is something like the components which have lower boiling point. Like by increasing the temperature to lower temperature itself, it starts boiling. Those components are called as volatile components. Based on the volatility, the components are being separated. So this is a simple understanding of a distillation, where we'll try to heat it up by using the thermal energy, and because of that, if the components based on its boiling point is separating it out, that is called as distillation. So in distillation, there are two phases which will be created. Like initial feed can be in a distillation column. Initial feed can be anything based on the it can be a raw input, like it can be a cold feed, or it can be any material which is coming from another process which is heated up to very high temperature. Then it can be in the form of vapors or mixture of liquid and vapors, or it can be directly a saturated liquid. It can be anything. So based on that, the feed can be, depending on the feed, here inside the column you have to create certain thermal energy, so that one of the component or two and more of the components can be separated out. So here the two phases which are involved are gas phase and liquid phase. So these are the two phases which can be involved in the distillation. So and here we also have the partial vaporization of it and partial condensation of it, because once we have vapor generated, once we start boiling, we create the thermal energy, the vapor start generated. Collecting it out the vapor, or to separate it as a, or collect it as a vapor, it's not that easy. So here we'll have a condenser setup. Okay, in the condenser, as we know, there are two types of condenser. We can have a partial condenser or total condenser, depending on the requirement, whether you want the product to be as a vapor or as a liquid. Based on the requirement, we'll use either partial condenser or partial or total condenser. Based on that, we can go with partial condensation or anything. Depending on the requirement of the product, we'll decide which kind of condenser need to be utilized. So here, the most probably understanding of a mass transfer, you need to know, for example, a distillation case, we'll have to create the thermal energy. Because of that, a different vapor state can be generated. That vapors need to be condensed, either partially condensed or totally condensed, depending on the requirement of an industry. So this is what the introduction to the distillation. So coming to the applications of it, so it can't be wrong if I say there won't be any industry without a distillation column, especially in a larger scale level. If you wanted to, if an industry is involved into purification or to separate any components, the distillation is a key element in that particular industry. So this is a very oldest operation, mass transfer operation for an industry. And the applications, when we when we talked about applications, majorly if you are having a product which is generated of constituting different components together, to separate those components you'll use this distillation. For example, aniline and nitrobenzene are the components. If you wanted to separate separate the aniline, you'll use distillation for it, knowing its boiling points. For an unknown component, let's say we are doing R&D and we have an unknown component, they have to do different, they have to play with different set of experiments to understand its boiling point. Okay, then only they can decide whether to go with that distillation column or not. And to recover a product, so if I have a product, if I done a process, I've got with a product, to recover main element from it. So for example, if you wanted to produce ethanol, it contains large amount of water from any let's say, for example, of a fermentation itself. So in that case, you can go with simple distillation and increasing the purity of the product. Rather than getting a product, it's not the point. The value of a product will be depending on how much purely you're preparing it. So, in order to maintain the purity, an industry may ask you to prepare it a 99% or 95% purity. Depending on the requirement, if you wanted to get a pure product, you will go with distillation. So, these are the different applications which you can talk about distillation. So, the main application of a distillation is in a petroleum industry. As petroleum, we understand as crude oil having thousands of products in it. It's not easy to separate all the 1,000 components. Then they'll go with a type of a distillation is called as fractional distillation, where you can get different fractions of the product. So the key element in the petroleum industry is a distillation. So it's also called as, that's why it's also called as a workhorse of chemical industries, because whenever you talk about a pure product, a separation of a product, separation of a component from a given mixture, first thing which will be tried by the industrial person is a distillation, because this can be distillation columns will be available. No need to make any changes, no need to buy any new equipment, only need to create the set of thermal energy inside the column to separate the product or separate the pure component depending on the requirement. So that's why it's called as workhorse of a chemical industry. So coming to the distillation, the main important point which you need to understand is to create the VLE data. VL is nothing but vapor liquid equilibrium. Inside the distillation column, we have to create the equilibrium between vapor and liquid, so that you have to create the stages in between the distillation, so that maximum concentration gradient can be created in the distillation. Rather than it being empty, you will create different number of stages in it. In each stage is behaving like a column again. So here in these stages, you are creating the equilibrium between vapor and liquid. So here you are creating a medium to have contact between this vapor and liquid, so that maximum amount of the concentration gradient can be created. From that, maximum amount of the pure component can be separated out. So this is what is called as creating vapor liquid equilibrium. So here in the to create or to generate this vapor liquid equilibrium data is very important to understand how many number of stages or how much big a column I need it to understand to get a proper product percentage. Like if you wanted 99%, how much big the column should be, how much number of stages I need to maintain inside the column, so that I can have the proper separation of the component. So this VLE data generation is very important. This VLE data can be generated either by the experiment. If you have a small setup, you can have the feed whatever you have, that you can experiment it, you can experimentally theoretically generate the data. And second one, thermodynamic models. We have different models which can be used to generate this data based on knowing what kind of components you have in the system. Third one is Raoult's law. Raoult's law is very important property for important to understand in terms of distillation. Raoult's law can be used especially for the ideal solutions. So this Raoult's law can be utilized to generate the VLE data. VLE data is nothing but vapor liquid. As we understand, vapor generally denoted by Y. Liquid composition will be generated by X. If you are generating VLE data, you are generating X versus Y data, which can be further utilized to understand the number of stages, how many number of stages I can create inside the column. This is what we are creating. Okay. So fourth point is relative volatility. Relative volatility is a ratio of volatility of the components. As we understood already, volatility is talking about boiling points. Boiling points of the components which are available in the given mixture. The ratio of those boiling points will give you the relative volatility. For a simple understanding, higher the relative volatility, better the distillation to be processed. So whenever we are doing whenever you are creating or when you are trying to understand how to separate an unknown mixture, these are the 4 properties which you can analyze it, so that we can have the better understanding whether we can go with distillation or not. For example, in a chemical engineering, degrees of freedom is very, very important. Normally, degrees of freedom, which can be denoted by capital F, is a function of number of components which are involved. P is number of phases plus 2. For example, if we take a VLE system, VLE is like vapor and liquid. Okay, so there are two phases, that is X and Y. You have vapor and liquid. So number of phases will be 2. Okay, so for if an example in the distillation column, I am taking a binary mixture. Binary in the sense you have two components in the mixture. So in place of C, I can write 2. For a given mixture of two components, if I try to understand the degrees of freedom, the value will be 2. That means I need to know the two variables for a given system so that I can understand the whole system of a distillation. So this is the importance of degrees of freedom in the system. So I hope the VLE is also clear to understand how the VLE is importance in terms of distillation. Just if I wanted to clear it out, VLE data is very important in order to have a clear picture for a known sample or an unknown sample, how to get or how to know how to solve or how to create the concentration gradient inside the distillation column so that we can have the better or easier the separation using distillation. So this is what the importance of VLE. VLE is nothing but vapor liquid equilibrium. In each stage you are trying to create the gradient of vapor. You're trying to meet vapor and liquid on the stage. So how many stages I need to create inside the column so that I can have the maximum of pure separation, pure component separation. That is what need to be created by using the VLE data which you are generating, and that can be generated by these 4 methods. Whichever is relevant for your given system, that you can take it out. So next, as we are talking about Raoult's law, Raoult's law was first introduced in 1830. So where he has conducted different set of experiments by taking 14 kinds in 11 organic solvents. By understanding these solvents, he has generated various vapor pressure data. Okay, so this, by understanding the vapor pressure data from a various set of experiments, he has developed a different formula to understand how the vapor pressure will be important and how it can be understood for a liquid system. So, and most probably the Raoult's law can be used for the ideal solutions. Okay, for an ideal solutions only you can use this Raoult's law, and this is very important for creating or generating the VLE data. Okay, so as we understood, for the ideal solutions only you can use this Raoult's law, and ideal gas mixture, and from this mixture if you wanted to create or if you wanted to produce a pure component, okay, this vapor liquid data or vapor pressure data is very important. Okay, so the basic definition of Raoult's law is equilibrium partial pressure of a component in a given solution at a given temperature is equal to the product of vapor pressure in its pure state. If a mixture you are having, what will be the vapor pressure which can be generated for a pure state of that component, that multiplied by the mole fraction of the liquid, mole fraction of the component in a liquid phase, not in a vapor phase, only in a liquid phase. This is what the simple definition of a Raoult's law. For example, PA is a partial pressure, equilibrium partial pressure of a component. Here I am taking a simple binary mixture A and B. Okay, PA is a partial pressure of a component A. As the statement is given, that can be written as PAV into XA. PAV is a vapor pressure of the component A in purest form. If it's in a pure, how much of vapor pressure which can be generated by that component multiplied by the mole fraction of the component A in the liquid phase. That's why most probably in distillation this notation is very important. X is for the liquid phase, Y is for the vapor phase. Okay, so XA is talking about X as it's talking about the liquid phase, solute or a component which you wanted to separate it out, that component composition or mole fraction. So that is denoted by X. X and Y are the mole fractions. The composition or the concentration of the components can be denoted in a different ways. Okay, basically it can be either in terms of number of moles or mole fraction, or either in terms of a weight fraction or weight percentage. So depending on the requirement, depending on what property it is being given, so you need to change it in order to understand. Here XA is talking about mole fraction. In your system, if the composition is given in terms of weight percentage or weight fraction, then you have to convert that into mole fraction. Then only you can use this formula. Simple formula: partial pressure is equal to vapor pressure into mole fraction of the component in liquid phase. This is very important. Most probably whenever you are saying Raoult's law, you'll only say partial pressure is equal to vapor pressure into mole fraction. You should not say that. You should precisely say it's a mole fraction of, mole fraction of the component in the liquid phase. Then only you can write XA. Okay. Similarly, if I wanted to write it for the component B, I can write it as PBV into XB. Okay. For a binary mixture, most probably the mole fractions, sum of mole fractions, that is XA plus XB, will be equal to 1. If A and B are the two components, in that case, the mole fraction of component A plus mole fraction of component B in the liquid phase will be equal to 1. So, in place of XB, we can write from here, XB will be equal to 1 minus XA. That you can substitute here. So, this is how you can calculate the partial pressure of the component B, knowing component B vapor pressure in its purest form. Then only you can use this formula. So this is for the component A, this is for the component B. This is a simple formula for the binary mixture. Depending on your depending on the system, depending on the number of components, you can go with and you can derive this Raoult's law. So next, other formula which can be used, rather than knowing component in the liquid phase mole fraction, I know the component mole fraction in the vapor phase. I know YA rather than XA. Then which formula I can use it? Okay. So basic simple law, that is Dalton's law. Dalton's law states that total pressure is equal to sum of partial pressures. If I have two components A and B, partial pressures which will be generated inside the displacement column, sum of the partial pressures if I add, I'll get the total pressure of the binary system. So in that case, by using that, I can calculate knowingly, if I know the mole fraction of the component A in the vapor phase, I can use this formula. That is, partial pressure is equal to total pressure. Total pressure, how to calculate it? You can calculate like this. Sum of the partial pressures and into mole fraction of component in the vapor phase. This is the formula for the component A. Okay. So if I wanted to write it for the component B, I can write it as here itself. So PB will be equal to YB into PT. PT is the total pressure. So these are the two formulas which you can use it. If you know the vapor pressure, if you know the total pressure and the mole fraction of the components in a vapor state, then you can use this. If you know the vapor pressure and the composition of the component in the liquid phase, you can use Raoult's law. Raoult's law states that partial pressure is equal to vapor pressure, PAV. V denotes it, vapor pressure multiplied by XA. This is what the formula. Okay. So you can use these two formulas to understand the partial pressure or vapor pressure which can be generated inside the column. Vapor pressure is nothing but, PAV is nothing but how much of pressure generated by the component A in its vapor state. This is very important. Based on that only whether the component is boiling or not will be decided. So to understand these properties are very important. So now if I know this is simple Raoult's law and this is for the component A and this is for the component B, as we earlier written, this is for the partial pressure, knowing vapor total pressure and the mole fraction of component A in the vapor state. This formula can be used. If you know in the liquid state, you can use this. If you know in the mole fraction in terms of vapor state. So this is what the formula. So if I equate, let's say this is equation number 1, this is equation number 2. Let's equate this. That is PA, you have PA equal to PAV XA. Other equation you have PA equal to YA into PT. Okay. So PA as is there. I can equate these two. So I'll have PAV into XA is equal to YA into PT. Okay, so from here, either if you wanted to know XA or if you wanted to know YA, depending on your unknown, you can go with. For example, I doesn't know YA, I can calculate it as PAV XA by PT. Okay, similarly, I can write it for the component B. YB will be equal to, in place of A, I'll write B, as I'm writing about component B, PBV XB by PT. PT same. PT you can write it as sum of partial pressures, PA plus PB. Okay, the same thing which we got. As we understand, sum of mole fraction in the liquid phase is equal to 1 for a binary mixture. Similarly, you can write it for the vapor phase. That will be YA plus YB will be equal to 1. Okay. So, from that, if I substitute the equations, substitute 5 in 6, then I can get it as YA plus YB equal to 1. In this place, I am writing PAV by PT into XA plus, from this, PBV by PT into XB is equal to 1. So after again here, if I wanted to write it in terms of only one mole fraction I know. So in place of XB I can write, in place of XB I can write 1 minus XA from this equation. So here I can substitute that. So that is what here we have done. So after minimizing, after reducing it, we'll get this equation. That is, if you know only the total pressure and vapor pressure generated by component A and component B, you can use this formula to calculate the mole fraction of the component A in the liquid phase. Okay. So if I know XA, how to calculate YA? We already done it. So we have YA is equal to PAV XA by PT. First you can calculate XA, substitute here, you can calculate YA. So this is how we can generate the vapor liquid equilibrium data by using Raoult's law. So this is a very important step. If we move forward, like to understand actually how a distillation column works and all, this plays an important role. Okay. So the next concept is relative volatility. As we understood, volatility, it talks about how easy the component can be separated out by boiling. Even at a minimum temperature itself, it starts boiling. So that component is a volatile component. So volatility of a component, this is a simple definition. Partial pressure by the mole fraction. Partial pressure by the mole fraction. For the component A, I'll write A. For the component B, I'll write B. Okay. So relative volatility definition, if you wanted to understand, this is a ratio of and relative volatility is denoted by alpha. And if you are writing for the component A and B, you will write alpha AB. That will be the ratio of volatility of A to the volatility of B. Then you can write it as PA by XA by PB by XB. So that is what here we have written. So this again you can reduce to PA XB by PB into XA. This is what one of the formula of relative volatility. Okay, so that formula can be even reduced by substituting this. We know that partial pressure is equal to total pressure into mole fraction of component in the vapor phase. Similarly, if you substitute, this is the formula which you will get. Depending on the data available, whether if you have partial pressure data, you can use this, or if you have mole fraction data, you can use this. These are the two formulas which can be used to understand the relative volatility. Generally, the alpha AB, why we need to know this? Because higher the volatile component, volatile component you have, it's easier to separation. So, alpha AB, if it's greater than 1, then your separation is very easier or very simpler using distillation. Generally, alpha AB greater than 1 only preferable to go to distillation. So, if you have an unknown sample, you have to generate all this data and you have to calculate this alpha AB value and to know whether you can use distillation or not to separate this mixture. That is the importance of this relative volatility. So, if from this relative volatility, you can also generate the VLE data. Vapor liquid equilibrium. That means X versus Y data you can generate it. So from this formula can be reduced further to this formula. The formula is simple. Y is equal to alpha X by, or if you're writing for the component A, you have to write A and all. I'm simply writing Y is equal to alpha X by 1 plus alpha minus 1 into X. Okay, if you doesn't know, if you doesn't have the VLE data, how to process further? So this data is nothing but the equilibrium data. This can be used to calculate the number of stages, number of equilibrium stages inside the column. So I can assume the X and X values starting from 0.1. Mole fraction cannot be greater than 1. So I'll calculate it from 0.1, 0.2, 0.3 and so on 1. So I'll substitute it here. Knowing alpha value, I should know alpha value. Generally, alpha value should be greater than 1. It will be given for a system. You can assume it, or by calculation, you got it as less than, greater than 1, let's say 2.5. So you will substitute here 2.5. And in place of X, I'll substitute 0.1. Here, I'll substitute 0.1. Alpha is 2.5, 0.1. And I can generate this Y data. Okay, in and distillation, this data generation is very important, as we already understood, that is X versus Y data. Okay, so this is what called as operating line. This is called as equilibrium data which you are generating. This is that curve. Generating this curve is very, very important. So this VLE data plays an important role to understand the number of stages or equilibrium stages which you have to create inside a distillation column. Right? So this is what we understood in this distillation, the major when to use distillation and how to process how to know whether the distillation is preferable for an unknown sample or not. Most probably industrial level, already they'll be having a proper setup for a separation of components. Maybe if you're doing R&D, then you have to do or generate theoretically data by using Raoult's law, maybe by using Dalton's law, by using alpha AB, that is relative volatility. Based on that itself, you can get to know whether to go with distillation or not to separate a given unknown sample. For a known sample, they'll be having all the data available. So it's easy to run, like petroleum industries and all, they'll have huge data. So for there won't be any changes in it. Depending on the crude oil properties, there will be some of the other changes we'll be doing in the pre-treatment. But in a distillation column, if you maintain that temperature, you'll have that component separation. So that is how distillation plays a major role in various industries, including the major revenue industries like petroleum industries, petroleum refinery industries, right? So in the coming sessions, we'll be talking about more deeper, like what are the different types of distillation, how to calculate the number of stages and all. So this is what the introductory part which you need to know if you wanted to process further, or if you wanted to get on to like how to solve a distillation problem if it's given industrial level. Yeah, so this is what the overall gist of an introduction to the distillation, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.